Okay, so let's talk a little bit more now about Newton's second law. As a reminder, trying to solve the cause-effect problem. To do that, you have to have the acceleration. The equations of motion can provide the acceleration sometimes. Excuse me, if you know enough about what's going on with the body. If that doesn't work, yeah, you're stuck with Newton's second law, which we now can express in terms of an equation that says if we vector sum the forces acting on a system, and the system is typically one object, but it doesn't have to be. But if we vector sum the forces acting on, by the way, I should emphasize on a system, not by the system, but on the system. Really important, make that distinction. We do that, we get the mass of the system times the acceleration of the system, which is what we're after. And so we could write this as vector A is the vector sum of all forces acting on the system divided by the mass. Okay, so I typically write it like this, like most people, but you could express it like that. Okay, now, one of the things that we want to make sure is if we're going to vector sum all the forces that act on a system, what are those forces? You've got to be able to identify them. So our first job when we're doing these problems is, well, I mean, once you have decided that you need to vector something, once you've decided that you need to apply Newton's second law, the first thing you got to do, identify the forces that act on the system. And then you must have at least a sort of a checklist of forces that could be acting on the system, and you go through that checklist, okay? Now, the checklist I'm going to give you for this semester applies for Physics 2A. In Physics 2B, you'll come up with a couple more, the magnetic force and the electrostatic force. But we don't do that in Physics 2A. Instead, we have different forces. All right. And one of the forces, well, actually, we've already identified two forces. One is gravity, and two is the normal force. And so I thought I would spend some time talking about these two today, and then I'll bring up tension here if we have time. Okay, so let's go ahead and move this. And let's talk about gravity. All right. So Newton was involved in a lot of things. I mean, the guy is an absolute genius, maybe the greatest physicist of all time. I certainly think so, and I think most people do. And not only did he come up with Newton's second law, but he also came up with the universal law of gravitation. And essentially, he was the one that came up with the idea that whenever you have two forces, or two masses near each other, they attract each other by a certain amount of force. And he wrote down the actual interaction. He said that if you have a mass here, we'll call it M1, could be a book, could be, whatever. You have another mass, M2, okay? So let me go ahead and simulate this. Okay, so I place this body here and this body here. And these two bodies here, this is M1, for example, this is M2, they attract each other. They pull on each other. That pull is a force. Okay. So let me go ahead and here. And the question becomes, well, whenever you're doing a force is a vector. There are two things you have to know about the force, or at least going to have to try to figure out. How big is it? How much force? And which direction does it point? It's a vector. It's going to have a magnitude and a direction. So the first question is that in which direction do the forces point? Well, this mass here is going to pull on this one. So what I typically do is I put a thumbtack through this one that fixes this one in location so I can just concentrate on this. And remember, we're trying to find the forces acting on a system. M2 is our system, okay? This force pulls on it in this direction. It's attractive. Okay, so we know the direction of the force. How big is it? Well, Newton looked at it and said, wait, we did enough experiments where he was able to determine that the force of attraction between any two bodies, M1 and M2, was equal to G, and this is just a number. I'll write it down, but we're not going to worry about it. So G in SI system is 6.67 times 10 to the minus 11. This is SI. But again, we're not going to worry too much about this particular details. All right. Then he had these are the two masses involved. And this is R squared, where R is the distance of separation. And so because R is R squared, and you're dividing by R squared, as the objects move further and further apart, the force between them drops off dramatically. And we expect that as two objects get further and further apart, you don't think that they'll attract each other as much. And it falls off by R squared. Okay. So, and by the way, what is the force on M1 due to M2? So in other words, if this is the force on M2, I can write this as M, this one here, then what is the force on this one due to this body? So I'll pin this one down. And now I want to know what the force is on this one. Well, it's attractive, so it's pulling. We'll call this F1. And we'll put in here G. And in this case here, we have M2, M1. The masses are switched, divided by R squared. However, if you multiply M1 times M2, it doesn't matter if you multiply M2 by M1. This is the same as this. So these two bodies attract each other with the same amount of force, just in opposite directions. And that's a consequence of Newton's third law that we'll cover a little bit later. Okay, so ultimately, right now, all I want you to understand is that two bodies attract each other through the force of gravitation. And that this is the equation that describes the amount of force between them. The direction of the force is attractive. So whatever body it is, it's directed, it's pulling. So the force is directed towards whichever body is creating the force. All right. Now, here's another thing that's kind of interesting. Suppose that we are very close to the surface of the Earth. I do more problems with this, but right now we're going to step away from this equation anyway. Okay, so now we're very close to the surface of the Earth with a body, which is almost all of our physics problems that way. Okay, so here's the Earth. And here's the center of the Earth, the center of mass. And well, let's suppose that we have our red pin here, right here. What is the force of gravity acting on this marker due to the Earth? Well, the Earth has a mass ME. And of course, this is the mass of the marker. We'll just call it little m. This distance is the radius of the Earth, right? So what would be the force acting on this red marker due to the Earth? Let's write down the equation. Newton said that the force of gravity acting on the red marker is equal to the big G, that number, we don't care about it, but it's a number, times the mass of the Earth times m divided by the separation. Well, the separation is between the centers of mass, which is, for all practical purposes, r speed. And this is going to be squared. Now I notice something. Suppose that I have another mass nearby. Let's say it's over here. It's a watermelon. So what would be the force on it? Well, write it down. I would say, I'll use the red M here for the this body here, and this one has a different mass, green M. And so I write it down. Say, well, I put G. This is big G, M sub B, over R E sub squared times this mass. And I notice that no matter what mass I place near the surface of the Earth to find the force acting on it, this part of the equation is always the same. It comes out to the same value. Big G is 6.67 times 10 to the minus 11 everywhere in the universe. The mass of the Earth doesn't change. And the distance, as long as we're close to the surface of the Earth, is always going to be R sub E. So I can substitute my values. I'll let you do that on your own if you'd like to. But if I substitute the values, I'd have to look up on the web, find out what's the radius of the Earth in meters, mass of the Earth in kilograms, and big G. I would get a very special number. I would get 9.8, and the units come out to meters per second squared, which we call G. So in other words, I can write the force of gravity on any body, anything near the surface of the Earth as simply force of gravity equal to M times G. Now you might think, well, that's great, but is this a coincidence that this comes out to 9.8 like before? Well, let's assume that we have our body in free fall. We'll let go of it. So over here, I have my body, my marker, and it's in free fall. Therefore, the only force acting on it is gravity, and I'm saying that that force is equal to mg, the mass of the body, times that g number, 9.8 meters per second squared. And yes, we're using 10 for the purposes of simplicity. What is the acceleration? Well, the acceleration is going to be given by Newton's second law. We vector sum the forces acting on the body. It's mg, and it's pointing down. And that's the only force. That is the sum of all forces. The negative sign indicates the direction. And that's got to equal to the mass times the acceleration. The mass cancels. And we get that the acceleration is equal to g downwards. So it works. It makes total sense. It's not an accident that we get the same value. Okay, so the lesson learned on this basically is one, when you have normal everyday objects that we're going to be doing 90% of the time, 99%, well, 95% of the time, the force of gravity can be simplified to m times g. You don't have to use the general equation here. You can use the simpler one. This is the magnitude, and the direction is straight down towards the center of the Earth. Okay, so that's the force of gravity. Then we also have the normal force that we talked about last time also. My body here, it's not accelerating. It's got the force of gravity acting down, but it's not accelerating. And you know from yesterday that if a body is not accelerating, the net force must be zero. In other words, all the forces must vector cancel. Well, the only way for the forces to vector cancel is to have another force pointing up of the same magnitude. And that force is provided by the table, and that's called the normal force. And the word normal, as I mentioned, means perpendicular. And the perpendicular is perpendicular to the surface creating the force. Okay. So I'm going to now show you an example. Bring this thing out. So now I have what we call an inclined plane. All right. And I can place my, oh, shoot, I missed the part. Where did it go? Now I placed my cart on here, and right now the cart is not accelerating. Therefore, whatever forces are acting on it, they must vector cancel. The force of gravity points straight down. There's a normal force that points up perpendicular, but it's not accelerating. There's another force I'm pushing on. So we call this an applied force. And that's just an explicit direct push or pull stated in the problem. In this case here, I'm actually pushing on the thing up the ramp. My combination of this force, the normal force, and gravity must all vector cancel. When you sum all those forces, they must sum to zero, vector sum to zero. Now look what happens though if I release my force. If I let go, the normal force cannot offset gravity. Why? Because the normal force cannot point straight up in this case, it points perpendicular to the plane. And therefore it can't offset gravity. Therefore you end up with a net force and therefore an acceleration. Okay, so let me diagram what we had up here. Okay, so let me diagram this. This is what you saw. I'm going to draw it kind of in the opposite direction. So it's easier for me to draw this way. So here's our inclined plane, okay? And then I had that object on there, my little cart. This is my mass. What forces were applied to this? Well, there was gravity. That points straight down and it has a magnitude of mg. Do not put a negative sign on g. G is the positive quantity, 10 meters per second squared, or 9.8 if you're doing homework problems, okay? The normal force is not straight up. It's perpendicular to the surface. So it points like this. It's a little bit large. These two forces alone don't vector sum to zero. In fact, we could do the parallelogram method, form a parallelogram, and we would see that we have a net force, we vector sum these two, the sum of those points from the what? The tails to the far corners. And this is our F net. Net force. The net force is not a force acting on the system. It's the vector sum of all the forces that act on the system. Okay, so make sure you understand that. Right now, there is a net force acting on my system. The system must accelerate. Newton's second law. Remember, that was one of the four kind of postulates that we made based on Newton's second law. So right now, this object would just accelerate down the ramp. We saw that. To keep it from going down the ramp, I would have to apply my own force equal and opposite to the net force. Now, when I vector sum these three forces, these two vector sum to this one, we'll call this one F prime. And then when I add, this is the force of me, or let's call it an applied force. But when I take F prime and I add it to this one, they're equal and opposite. All the forces vector cancel, they go to zero. And in this case here, the object does not accelerate, which means it doesn't change its motion. Since it was originally not moving and its acceleration is zero and therefore doesn't change, therefore it never does move. Okay. So let's go ahead and sort of tabulate what we have learned so far about the forces we have. Gravity. It has an amount mg and it points down. Straight down. And of course, this is assuming that we're talking about objects near the surface of the Earth. We're not talking about two different planets. All right, now, what about the others? Well, let's see, we have a normal force. We don't know how big its force is. It depends on what other forces are acting on it. Okay, but we do know its direction. It's perpendicular to the surface that's creating it. And then we also have an applied force. Oh, I should put our, I usually use F of G for gravity, F of N for normal, and then we have an applied force. And an applied force is just a force stated in the problem directly. A man pushes on a box with a certain amount in a certain direction. You know, explicitly stated. I give this the value FA. Sorry, the variable FA. There's no way of knowing the amount or direction because that can vary depending on the problem statement. Okay. I'm going to introduce one more. There's one more force we're going to worry about in the short term. Okay. This mass is not accelerating. Force of gravity is acting on it, pulling it down, but it's not accelerating. There must be a force heading up, and that force is provided by this string. This is a pulling force. It's pulling up because you can't push on a string. Well, you can, it won't do anything with it. So this is a new kind of force. This is called tension. And so we have tension force. Like the normal force, how big it is kind of depends on the other forces acting on the mass. But one thing we do know is that it's along the string, along and away on the string. So the direction is along the string and away from the body. In other words, because it's a pulling, you can't push towards the body, you can only pull away from the body. And this will do it for now. We do have force of friction coming up. That'll be in a couple of lectures. And then we have a buoyant force, which comes in towards the end of the semester. And that's pretty much about the only forces we deal with in this class. Oh, spring force. Yeah, the force due to a spring. I can't forget that. Okay. Luckily, next semester in physics 2B, we really only have two more forces: electrostatic, and a magnetic force, whatever. All right, so let's do a simple problem. This is the first problem that we're going to do that involves the full extent of that little handy dandy diagram. Okay, so go ahead and draw that up again. Oops, a little better. Acceleration, Newton's second law, equations of motion. This is vector sum of the forces is equal to the mass times acceleration, but we have to have this expressed in words. The vector sum of all forces acting on a system that you define is equal to the mass of that system times the acceleration of that system. Equations of motion depends on the kind of acceleration. We've only done linear constant acceleration, so that's what we're going to kind of hold down for the time being. Those equations look like this. D is V naught T plus 1/2 AT squared, and V is equal to V naught plus AT. There's a third equation that you could write down from these two, that V squared equal to V naught squared. It's awful, stay away from it, okay? And now we're going to solve a problem with this. So here it is, I'm going to state the problem. In fact, I'll even demonstrate the problem. We have a mass here, mass M. Set it here. And this distance right here from here to here is 30 centimeters. Now let go. I notice it takes 1001, a little over a second. We'll say it's 1 second for it to go 30 centimeters. Okay. The question is, if that's the case, what's the angle of inclination? Only one angle produces this distance, this displacement in that amount of time. What is that angle? Now, calculationally, this is a little more difficult than most problems that you're going to encounter. But what is most important is to know how to systematically proceed. We worry about the difficulty of the mathematics when we get done at the end, okay? So let me go ahead and draw this out. That's terrible. This is the angle theta. We don't even know what that is. We're trying to figure it out. And we have our mass. And we know one thing. It travels down 30 centimeters, which is 0.3 meters. I like to convert everything to MKS at the very start. And the time it takes is about 1 second. I don't know the mass of the cart. I'm going to not worry about that for the time being. The question is that, oh, and by the way, initial velocity is 0, right? It started from rest. So it started with no speed at all. And now the question is that, what is this angle? And you think, forget it, I'm done. I don't know what to do. I know what you're thinking. I don't know what I'm doing. I have no way of figuring it out, okay? Well, I'll tell you what, let me go ahead and, I'm gonna draw this a little larger. Just notice on the screen, it's kind of small. So let me go ahead and draw this again. Start over here and draw it really big. And this angle is obviously exaggerated. It's a little exaggerated too much of there. Pipe it down a little bit. Okay, so I have my mass. And my initial velocity is 0. The time is 1 second. That's kind of all I know. So what do we have to find? What's the holy grail? What's that one physical property that we must find somehow? The acceleration. A lot of students will say, well, it's 9.8 meters per second squared. No, this body is not in free fall. There are other forces acting on it other than gravity. This is free fall. This is not. So do not assume anything about the acceleration. So the first thing I always do is I look at the equations of motion to decide, because it's easiest to tell if they will tell me what the acceleration is. We know the initial velocity. Oh, and I didn't mention that this thing traveled a distance of 0.3 meters. We know the initial velocity, and we know the distance of travel and the time. Can we get the acceleration from our equations of motion? Well, let's try this one here first. The displacement is 0.3. Positive because the displacement of the object is in the positive direction. Oh, I did not mention, but we are going to slope our axes like this, right? So this is our y direction. This is our x direction. And why? Because the acceleration is down the ramp. We always slope our axes along the direction of the acceleration. So this is a positive 0.3. And this is equal to the initial velocity, which is 0, times t, which is 0, plus 1/2 times the acceleration times the time squared. And their acceleration, therefore, is 0.6 meters per second squared, and it's positive. I left the arrow on top because I wasn't, well, I could have guessed that the acceleration was down the ramp, but I left it on there anyway. So I got a positive answer that tells me what the acceleration is positive. Okay. So now I applied the equations of motion. I have found the acceleration. How do I finish the problem? I finished the problem by applying Newton's second law. All right, now I'm going to apply Newton's second law. To do that, I have to vector sum all the forces acting on the body, and I have to know what they are. Okay, and in this case, there's only 2. So I'm going to go ahead and kind of clean this up a little bit. It's gotten kind of messy. Well, I don't have to do too much. Take out the displacement. We use the displacement. We found the acceleration. We don't need it up there anymore. So we have the x direction, y direction. And now the question becomes, if we're going to vector sum the forces acting on the body, what are they? Well, we go through our little list. Does gravity act on the body? Yes, it does. It's in a gravitational field. Therefore, we have this gravity, but it points straight down. It doesn't point like this, it points straight down. We also have the normal force, and the normal force points perpendicular to the surface along the y direction. And now we have these two forces, we have to vector sum them. This vector here is okay, it's fine. This one is a bad vector. It's a bad vector because it doesn't point along our preferred directions. So we have to find its components. If this is the angle theta, then this is also theta. Take my word for it. I'll prove it later. By the way, this is a fairly complex problem. I'm starting off because I want to show you, I kind of should have mentioned this, that this thing here really, really works well. You don't want to panic when you encounter a problem. Just do it and you'll get the answer, okay? So now I need to find what? I need to find this component. This angle symbol touches, so this length here is mg cosine of theta. Touches cosine, touchy cosine. And if this is mg cosine theta, this is mg sine theta. And now I don't need this one anymore. Let me vector sum. Oh, this is a vector equation, means it applies in any direction. It applies along the x direction and it applies along the y direction. So let me apply it along the x direction. What are the forces? Oh, I need to write down. We're going to vector sum the forces along the x direction. We'll set that equal to the mass of the body times the acceleration along the x direction, which we already know. What are the forces that act along the x direction? There's only one. You think, well, what about this one? What about that one? Those don't act along the x direction, they act along the y direction. This is the only x one. It's mg sine theta. And it's the only force, so it is the vector sum. The masses cancel. You see, that's another lesson to learn. Just because I didn't give you the mass doesn't mean you stop. You say, okay, I'm just going to call it m, and I'm going to keep it m, and hopefully something happens in the end and it'll disappear, and it did. And guess what? We get g, which is divided by g both sides. And we get that the sine of theta is equal to the acceleration that we found of the body divided by, or I should use 10, I guess. This is 0.06 meters per second squared. This is 10 meters per second squared. And I get 0.06. All I have to do is take the inverse sine of both sides, the arc sine, I'm done. So theta is equal to the arc sine of 0.6 over 2, or actually just 0.06. And you're done. there it is. I'd go to rapid tables, the inverse sine or arc sine. I would type in 0.06, hit the little button, and it'll tell me what angle it is. This is a fairly sophisticated problem, but notice that, and there's some mathematics in here, but notice the progression. This is what I really want you to come away from with this problem, is I countered this problem that made no sense to me, like, oh my God, this thing looks really horrible. It's like I will never be able to solve it, but I don't panic. I instead say, okay, whatever it is, I got to find the acceleration. And there are two ways of doing that. The first one I always try is the equations of motion. So I did. I decided, hey, man, I'm just going to go ahead and see if this will work. I put in my displacement, my initial velocity, and my time, and guess what? I got the acceleration. Good. So I applied my displacement equation of motion. I found the acceleration, and then I finished the problem by applying Newton's second law. That was all this stuff, and I was able to find my angle. Okay, so you will be accounted for learning how to do this problem, but right now we're going to kind of go back a little bit and start more with the fundamentals. So it'll be the next few problems will probably be easier, but I just kind of wanted to show you how this thing works, and it does work. Now, what happens if the equations of motion don't work? Well, then I go to Newton's second law. I identify the forces, I find the acceleration, and then I apply the equations of motion to predict what's going to happen to the motion of the body. All right, let's do some more problems. What I have is the infamous, no, it's famous. It's nothing hard about it. The elevator problem, and this is really common. Okay, so and there's one I think on your homework. So I have an elevator, and hanging from, well, let's see here. I'm going to have it hanging. Yeah, okay. So hanging from this elevator is a mass of 2 kilograms. This is a string, and the elevator is dropping down at a constant velocity. So let's just write this. And the question is, what's the tension in the string? Now this 2 is 2 kilograms, it's the mass, okay? What is the tension in the string? They go, oh my God, I don't know what to do. Well, first of all, do we know the acceleration? And the answer is yes, we already know it. The acceleration is 0. This object is moving down at, this whole system is moving down at a constant velocity. There is no acceleration. A is 0. Therefore, we can apply Newton's second law now to find our unknown force. You're going to vector sum all the forces that act on what's the system. Well, I think this will be the system right here. So it's going to be the on the ball. It could be a bowling ball, although 2 kilograms is awfully light. And that's equal to the mass of the ball, which we know. That's the acceleration of the ball, which is 0. So now the question is, what are the forces that act on the ball? Well, let's see here. Let's go down our list. Does gravity act on it? Yes. Gravity acts down. It has an amount of mg. Well, the mass is 2 and g is 10. So this is 20 newtons. Get used to that. Okay. The force of gravity is not 2, that's the mass. You got to multiply by g to get the force. And that's 20. And again, of course, if you're doing a homework problem, you want to use 9.8, not 10. What else is there? Is there a normal force? No. There's no surface supporting this ball. So there's no normal force. Is there an applied force? No, the problem doesn't have me pushing on it or pulling on it explicitly. Is there tension? Yes, there's a string pulling up on it. And so there's this tension force, F of T, and it's got to lift away from the ball because you can't push on a string, you can only pull with it. All right, now we can vector sum our forces. F of T is positive. Mg is negative, and that's equal to the mass of the body, which is 2, times acceleration, which is 0. And this tells me that the tension force must be equal to 20 newtons. And oh, I know it. I haven't gotten into describing how big the what a newton is. We'll do that in a second. But this newton is the SI or MKS unit of force. I'll describe in a moment here about how big a newton is. So I don't know how I forgot to mention that. I got to let it. Okay. Therefore, this is the tension. Notice the tension is equal to the force of gravity. Has to be. This tension has to vector cancel this one to produce a 0 acceleration. So that makes sense. Okay, now let's change it a little bit. Okay. Now, instead of this elevator moving down at constant velocity, it's going to accelerate upwards at 2 meters per second squared. So it's doing that. It's ascending, but it's ascending with an acceleration. Now what happens to my tension force? Well, you probably figure by just visualizing it, if you're going to accelerate the elevator up, the string is going to get tauter. So it's going to have more tension. So let's find out. Again, we have force up is positive F of T minus 20 is equal to the mass, which is 2, times the acceleration, which is not 0 anymore. I'm saying it's 2 and it points up positive. So this becomes F of T minus 20 is equal to 4. Now when I solve, I get F of T is 24 newtons. So the tension force is now grown because we're accelerating the object upwards. Now, I'll let you kind of work out on your own that suppose the rope that's pulling up on the elevator, something has to be lifted up, snaps. In that case, this whole system accelerates down at 10 meters per second squared. It's in free fall. What happens to the tension then? You should be able to work this through and ensure that the tension force is equal to 0. I'll let you do that on your own. All right, let's talk about the Newton, and then we'll be done for the day. Okay, so force is measured in newtons in the MKS SI scheme. It's measured in dynes in the CGS, but we don't use dynes very often. You won't use it at all in this class. Okay, so how big is a newton? Well, a newton is about equal to a quarter pound. In the English system, this is the unit of force, pounds, which we all know is better than newtons because pounds, like the English system, cool. I like it. But no, we got to use the SI system here in this class. So what weighs about a quarter of a pound? Well, a hamburger. What else? Kind of a large apple, which is easy to remember because of apple, Newton, get it? Okay, so if you're wanting to know about how big a Newton of force is, put an apple in your hand, and what you're applying to that apple is about a Newton of force. So 100 newtons is a bag of apples, 100 of them. Very simple. So at any rate, this is the unit. Make sure you kind of get an idea that a Newton is about the weight of a hamburger. Then I should say a Newton, an object that weighs about a Newton is like a hamburger or maybe a large apple. All right. So 20 newtons, which we had in here, a bag of, that's kind of like one of those small bags of apples. I am done for the day. We'll pick up more on this. We'll do more problems to the next tomorrow, and then we're going to start to hammer on friction. Well, actually, we'll do more problems tomorrow, then I'll introduce friction problems towards the end of the day. Okay? We'll see you later.